So the equation of motion for the multi-story building is, let's have our simplest MDOF system. So a two-story building or a two-degree of freedom 2DOF system. And so let's have the simplest structure in formulating our equations of motion. In the two-degree of freedom system, we have a two-story building with the mass for the first floor and the second floor. Then we have also the height supporting the first floor and the second floor. So the simplest 2DF system that we're going to assume for this one, let's say, is for the undamped free vibration response. Free vibration response. So when we say undamped, it means that our coefficient for the structural damping is equal to 0. And then free vibration, it means that our dynamic force, P of T, is equal to 0. Or let's say, with our assumption now, um, let's include first the dynamic force. Undamped, but there is an application of the dynamic. So let's say there's a dynamic force for the first floor. Let's denote that as P1 of P, and then the dynamic force for the second floor as P2 of P. Obviously, if there is an applied dynamic force for our system, the structure will deform, something like that. Now, if you remember the 2DOF system or the SDOF system, we can try to simplify our representation for this one by using a lump mass model. So we have our mass 1 there, our mass 2. We have also the this one, the heights, and then we have the dynamic forces. And what are we gonna do next? We'll have an FBD of the system. So for this one, we're going to cut here and also there. So let's have first the FBD for this one. For that part, it will look like this. There is a dynamic force, P2 of T. If there is an applied dynamic force, we have the mass, and then there we have also the stiffness of the column. There is also what we call the inertia force for the second. And as well, we have the static force or the elastic restoring force for the second floor. Now, what will happen there if we are going to sum the forces? We'll have, let's say, if positive on the right, we have P2 of T minus the inertial force of the second floor minus the inertial force of they call this, of the second floor, and is equal to 0 under dynamic equilibrium. Or simply we can rewrite that as our the inertial force of the second floor plus the inertial or the static force of the second floor is equal to the dynamic force of the second floor. We have also the t there that is as a function of time. It denotes that these values are also changing through time. They are dynamic. Let's say this is our equation 1. Next is Now, since we have used this the FBD for this one to calculate the equation of motion, next one is we're going to have the FBD of that one to calculate the another equation of motion. Okay, we have our dynamic force for the first floor there, and then we have our inertia force for the first floor. And as well, we have our elastic force or static force for the first floor. Now, since this system is just a continuation of the this is a single system, but there is a separate. We try to separate the second floor and the first floor. What we need to do is that we need to also consider this static force present on this column coming from the dynamic force applied on the second floor. The direction for that one is towards the right. So we have also the static force there for the second floor. This denotes uh, that our equation of motion is equal to the inertial force for the first floor plus the we have the Fs1 or the static force for the first floor minus the static force for the second floor equal to P1 of T. This is our equation 2. Now let me rewrite that one as the equation of motion. Again, we have our equation 1 that is the inertial force for the second floor plus the static force for the second floor is equal to the dynamic force for the second floor. Now, if you remember, the inertial force is equal to the mass times the acceleration. That will become the mass of the second floor times the acceleration for the second floor plus the stiffness for the second floor times the deformation for the second floor is equal to P of, let's say, this is our equation 3. Now let's rewrite again our equation 2. We have the inertial force for the first floor plus the static force for the first floor minus the static force for the second floor is equal to the dynamic force applied on the first floor. We have the M1 U double dot 1 plus the K1 U1 minus, by the way, we forgot. No, this is not U2 if you remember. So let's go back with our lump model. That is the two-story. Okay. Now, if our system will move like this, now there is deformation to happen. The deformation for the first floor is denoted by, say, U1. And the deformation for the second floor is denoted by U2. Now, if you remember the formulation of equation for this SDOF under earthquake loading, the inertia force is moving from starting point, sorry, from starting point up to this point. So it is reasonable that our acceleration should be from the starting point up to that point. However, the static force, we assume that the structure move up to this point, and then because of the applied dynamic force, the at this point, the structure also move to the right. So it is then that the last or the lateral stiffness of the column supporting the second floor is being applied. So the distance there is just U2 minus U1. Therefore, the static force for the second floor is equal to, we have the stiffness for the column supporting the second floor times U2 minus U1. Same also here, we have minus A2 for the stiffness supporting the second floor times U2 minus U1 is equal to the dynamic force applied on first floor. If we rewrite this one in such a way, by the way, no, this is our equation. We can rewrite this one as U double dot times the mass of the second floor plus, if we distribute the lateral stiffness of the second floor to the following there, we have the U1 as the negative K2 plus the U2 times K2 is equal to the dynamic force for the first floor. And then this one, it will become the U double dot for the response acceleration of the first floor times the mass of the first floor plus, now if we distribute that one, let's say we can write it as U1 is K1, then we have here plus U2 times negative K2 plus U1 times K2 is equal to T1, or U double dot 1 times M1. Then when we just combine like this, so we have a U1 here and there. For U1, or the deformation of the first floor, we have this expression as U1 times K1 plus K2 plus U2 times negative K2 is equal to P1. Again, let me rewrite that again, once again. Okay, this one. Over this one, I just wrote first the equation 4 and then followed by the equation 3. So this is the equation we derived from the first floor, and then this one is from the second floor. Now, I would like to write this equation in such a way that in both equation 3 and 4, there is the presence of both the response acceleration for the first floor and the second floor, and as well the masses for the first floor and the second floor per equation. So for the equation 4, we can rewrite that as the response acceleration for the first floor times the mass for the first floor plus the response acceleration of the second floor times 0, and then plus U1 times K1 plus K2 plus U2 as negative K2 is equal to P1. That is our newly written equation 4. Now our equation 3, we'd like also to include the response acceleration for the first floor. So we'll have response U double dot 1 times 0. So U double dot 1 times 0, then it's just 0, and then we are left with this 1, diba? So that is just, they will look similar. We have also the U double dot 2 there times our mass for the second floor plus the U1 times negative K1 plus the U2 times the K2 is equal to P2. Now, we'd like to make these two equation. We'll try to make the two equation to uh, become a single equation, simplified a single equation. Now, what will happen if you look closely with this one, on this part and this part? Okay, we're going to apply the concept of matrix for this one. Now, what will happen next? We'll have our matrix now. We have the mass 1 for this one, and then there is 0 on this part, and then 0 and the mass 2. Then we have also our response acceleration vector, U double dot 1 and U double dot 2. Plus, we have our stiffness K1 plus K2, and we have our K. Oh, this is This is not K1. This part here, that is K2. K2 is negative K2. Because if you remember, where was it? This one. We have the U2 times K2, and then we have the U1 times the K2. So that should be K2. So we have here the negative K2 in the matrix. Let me change this one. This is K2. Then you have the negative K2, and then the K2, stiffness K2, times we have also our deformation vector. Here we have our U1 and U2. Then equal to the dynamic force vector P1 and P2. Now this part here, we call that our mass matrix. Let's say that the symbol for that is this one. This part here, we call that our stiffness matrix. Let's say our symbol for that one is this one, this K. And then for the mass matrix is this one, this M. This is our response acceleration vector. This is our deformation vector. And this is our dynamic force vector. We will continue with the formulation of equation in our next presentation or discussion.